Hi 253. In this video we're going to begin our work in section 10.4 with discussing conic sections. So we're going to consider curves which are the result of the intersection of two geometric figures, right? Two geometric notions. So let's start out with a definition. Conics or conic sections are curves that result from the intersection of a double napped right circular cone and a plane. The conics that we're going to consider are circles, parabolas, ellipses, and hyperbolas. But there are other conic sections, points, a point, a line is an example. Intersecting lines are also an example of a conic section. But these are the four that we're going to be focusing on. So first of all, what I want to address is this issue of what exactly is a double napped right circular cone. I think we all agree that we know what a plane is, but what is a double napped right circular cone? So let me show you exactly what that looks like. So the idea is that to generate what's called a double napped right circular cone, you start out with a line. Okay, and then what you do, you can call this like the axis line if you want, right? So this is the axis line. What you do then is you take another line and you intersect it with this one. Okay, and you can call this line the generator line, or the line G for fun. Now these two lines, they intersect and they produce this angle right here, and we'll call this angle theta. Okay, so what you do to generate a double napped right circular cone is you make sure that this axis line here is perpendicular to some respective plane or something like that. Just make sure that axis line is straight up and down. Then what you do is you take this line G and you spin it around the axis line like this. Okay, when you rotate it around like that, you end up creating what's called a double napped cone. And it would look like this. These are the two sort of sides of the cone. And it would look something like this, right? This is a double napped right circular cone. It's a right cone because the axis line, which is that line that you labeled the axis line, is right angled at the bottom, right? And that line G, the generator, is this here, this side, and then also the one that it swings all the way around, right? And it's a three-dimensional object. Okay? So let's see. So what does it look like when a plane intersects a double napped right circular cone? So here on the left, actually this top one, we don't have a double napped cone. This is actually just a single napped cone, meaning it's just the one part of the cone, just the bottom half. But over here we have the double napped cone. We have the top and the bottom. And when you start intersecting it with a plane at sort of different orientations, right, you get different results, right? So for example, this plane here, when it intersects the double napped cone, makes what's called a parabola. Yes, I know you've heard of that before. If you take the plane in this orientation here, you get a small circle. If you angle it a bit, you get an ellipse. Yes. If you take the plane and you sort of slice the double napped cone straight up and down, you'll get what's called a hyperbola. Okay, because again, the double napped right circular cone is not a solid, right? It's hollow on the inside, so you're just generating the curves here, the hyperbola, ellipse, circle, and parabola. Here's an example figure where you can actually see that the point is being generated when the plane passes through what's called the apex, or the point here where the two parts of the cone actually meet. And here actually is a single, like I said, example of how those curves are generated by that slicing action. So in your book, they have this figure 10.40, that shows you all of the slices that can possibly be made with the plane and the double napped right circular cone. They actually include nicely the point that can be produced, as well as a single line, right? That's when the plane sort of touches, or is actually, I should say it specifically, when the generator is contained in the plane. And then also when we have sort of this, you're slicing right down through the center of the double napped right circular cone. A nice animation that we actually have here for our I linked it to Moodle for you, so you can actually access this later too. But this animation sort of shows you that as the plane orientation changes, you get different curves being produced by the intersection of the cone and the plane. So that's kind of a nice little animation there. And you can pause it too. You can stop it somewhere, and then you have to reload it if you wanted to start the animation again. Okay, so let's see this. Oh, I included this just for fun because the idea of conics has actually been around for quite a long time. It actually was the Babylonians actually had ideas about conics in I don't know 100 AD or something like that, or even before then. So this idea of conics is not a new idea. It actually is one of the original branches of mathematics, and this was a page from the table of conics in the Cyclopedia from 1728, just for fun. So let's consider the parabola first, right? Of all the conic sections we're going to consider them one at a time and work with them and develop them from a geometric standpoint. So I know you already know what a parabola is, but the bigger issue is that the only way you know how to define a parabola is if you're living in the xy axes, right? You know that y equals x squared generates a parabola. But there's actually a geometric underpinning to what a parabola is, and it lives, that definition lives outside of working in the rectangular coordinate system. So the official geometric definition for a parabola is the set of points in a plane that are equidistant. That should be equidistant, not distance. That should be a t right here. So it should be that are equidistant from a fixed point, capital F, called the focus, and a fixed line called the directrix. Okay, so the question is now, what would that look like, right? And then can we write the equation of a parabola using this definition? So just to see exactly what that would look like, let's see if we can try to sketch it first before we go about trying to generate the equation. So the idea is we have some kind of line and a point. So I'm just going to choose a line and a point at semi-randomly here. Let's call this the line that we're going to be working with, the directrix, right? This is our directrix. And I'm going to call the point, the focus here, this guy right here. Okay, so that's going to be our focus. We'll call that capital F. Okay, well, the idea of a parabola is that it is all of the points that are equally distant from the directrix as well as the focus, right? So here, notice one obvious point is this one right here. That right there is a point on the parabola because it is equally distant away from the directrix as well as the focus. But notice that also, I have to do this very carefully, this is a point on the parabola. Also notice that its distance to the directrix is this sort of distance here, and the distance to the focus is here, and that's the same length, right? Okay, and we can keep going. How about there? Yes, that looks to be the same distance here to here, and of course because of symmetry you're going to get the same thing happening over here and over here. We have to do it very carefully, right? Okay, and so if we get this idea and we can connect the dots here, we're going to see what we get looks very familiar to us. Yes? And so that shape right there, that is the parabola, right? And so it's generated, notice, by a geometric definition, right? Not by working in the xy plane. It's simply the collection of points that are equally distant away from a line and a fixed point, F, the directrix and the focus. Okay, well, let's now handle this idea of, from this geometric standpoint, can we produce the equation of a parabola? Would it still work? Well, let's see if we can. Let's apply a set of axes here and then see if we can come up with an equation. So let's just for easiness, let's put our set of axes like this. Now there's absolutely no reason that I had to put them like this, right? Other than it makes the math we're about to do in a second a little bit easier. Okay? By the way, this focus is going to pass through the axis like that, right? It's actually living on that axis right there. Okay? So let's label this as the x-axis and let's label this as the y-axis. And let's see if we can now label some things. Since we're living in the rectangular coordinate system now, we can actually label stuff. So why don't we go ahead and label this point F as point P, comma, 0. We can do that because we know that this is a point living on the x-axis. Its ordered pair is a number and then 0. We'll also assume that P is positive for right now. Well, if that's the case and I label this point as P, comma, 0, then that means the directrix has to be what? It has to be, since this point is equally distant away from the directrix and the focus, it has to be x equals, because it's a vertical line, and it's what? P units away from the origin, yes? Because this is P units away from the origin. So that has to be x equals negative P. Okay? So to generate an equation, let's see what happens. So let's consider the following. If we put this point xy on the parabola. If we just say xy is a point on the parabola, then what we know for sure is the distance between that point. Let's just put it somewhere. How about we put it right here? Yes? I'm just picking one. Doesn't matter which one I pick, I'm just going to pick that one. So if I label this as the point xy, then what I know is the distance between this point and the focus, and f, right? This distance right here, that's the same as the distance between the point and the directrix, right there. Yes, because that's the definition of the parabola. That's how we originally started drawing this shape here, yes? Okay, so we can actually use that here to construct the equation of this parabola. So notice that I've drawn this so that this point goes, the distance is calculated by going from this point directly to the directrix, right? Okay, so because of that directness over to the directrix, right, and this is a vertical line, I know that this is a right angle right here, okay, and that's going to be important for us in just a second, okay? So what we do know is how to write distance when we're working in the rectangular coordinate system. Do you remember the distance formula? We've got distance between 2 points. It's some scary square root thing, right? If you don't remember, I can write it as follows. So the distance between 2 points, we'll call them A and B, right, is equal to what? Actually, I have to be very careful. If you want to write this, you have to write it as the distance between two ordered pairs, right? Okay, so let's modify that slightly. So let's see. So if you want the distance between 2 points, let's call them A, B, and C, D. My pen is being terrible right now. This is awful. It's almost like it has a bad days or something like that. Okay, let's see. C, D. There we go. This is equal to the square root of A minus C squared plus B minus D squared. Remember that? So that means that I can write the distance between the point here, the point x, y, and f as being what? So that means it's the square root of, I have the ordered pair x, y, and the ordered pair p0, right? So I know this is x minus p squared plus y minus 0 squared. Okay, that's the distance between the point xy and the focus. But I know that's equal to what? The distance between xy and the directrix. Well, how long is that line segment right there? We don't have to use the distance formula for this. We can if we want, but we don't have to, right? Because what we know is that this length right here is x, and we know this length right here is p, right? Because it's p over, and this is x over, so that means that that's equal to x plus p. Good? Now, quite honestly, this is enough. This is an equation in x and p and y, right? And it could describe the equation of that parabola, right? Because it's true that the distance between the focus and the point on the parabola is the same as the distance between the point on the parabola and the directrix. But we never leave it written like this, it just looks too sloppy. So let's square both sides and clean it up a little bit. So x minus p squared plus, this is just y squared. That will equal x plus p squared. Okay, and we do a little bit more work because this still isn't clean enough. We could see that things would cancel if we just square stuff out. So let's square these binomials. So x squared minus 2xp plus p squared plus y squared equals x squared plus 2xp plus p squared. Some things cancel, namely these x squareds are gone. The p squareds are gone. Again, if I'm going too fast, pause the video, right? And what am I left with? I am left with, well, actually, I can make this look nicer, couldn't I? I could actually add this 2xp to this side and get something that looks familiar. Y squared equals 4xp. Now, this may not look completely familiar to you, but I think all would agree that a sideways turning parabola is supposed to have some kind of y squared, and it's supposed to equal some kind of an x, right? So this is semi-familiar to us. The only reason we're not really comfortable with this is because there's a p, right? The p right here is, remember, the distance from where? From the what we call vertex of the parabola to the focus, or from the vertex of the parabola to the directrix, right? Okay, so that's that distance p right there, okay? And notice that that value for p is actually determining what kind of shape of a parabola we have, right? So how far away you decide the vertex is from the focus, i.e. the same thing from the vertex to the directrix, that changes the shape of the parabola, because notice that p multiplies times the x and times the 4, right? So that has a direct effect on the shape of the parabola. This is just one kind of parabola we can get, right? Because we know there are actually lots more, and I just artificially chose how to put the directrix in the focus. I could have instead said that the directrix goes like this and the focus is here, yes? And what kind of parabola would we get then? It would be this shape, right? And that has a different equation than this. Okay, so let's see what the other equations look like. I have this nice table here organized for you to describe what the shape and equation is for certain parabolas. So we're going to have the vertex always be at the origin, right? And we're going to have the focus be in different orientations here. So the one we just arrived at was this first one right here in this first row, okay? Because our focus was at the point P0, if you remember, right here. Focus was at P0, directrix was at x equals negative P, and we came up with this equation. Similar constructions for these alternate forms here would allow you to get different equations. You would of course have different directrix equations. So if you want to maybe put a little sketch over here when you're taking your notes, you can do something like, this one opens this way, right? This one right here, if the focus is at negative P0 and the directrix is at x equals P, that one has to open this way, because notice that the focus is always going to be interior to the parabola, like that, right? Okay, so in the first one we had our directrix here, focus here, it wraps around the focus. Directrix is here, focus is here, it wraps around the focus. Same thing here, what would we have? Y equals negative P, that's down here. And the focus is here, yes? So that means our parabola would look something like this, opening up. And similarly, if we had y equals p, that's up here, and we have our focus here, our parabola will open down because it wraps around the focus like that. Okay, now all of these, like I said, are their vertexes at the origin, but if, let's say, we wanted to shift the parabola and have the vertex be at hk instead, we just need to perform what's called, remember, a transformation from 111. And that would mean we just replace x with x minus h and y with y minus k, right? So what that means is if you wanted to have your vertex be at hk instead, and say you wanted to use this first form here where it opens to the side, you would instead have an equation that would look like this. You'd have y minus k squared equals 4p, replace the x with x minus h. So you want to say x minus h, right? So that's going to be a opening to the right parabola with a vertex at hk instead of at 0, 0. From your textbook, this is figure 10.42. They've given you a nice little sketch here also, similar to what I just put here on the right in this little column here. I think these ones are just easier to remember briefly, but this one has all of the labels with the equations and of course saying that you have an either positive number here or a negative number. If p is negative, then you get a negative sign in front. Okay, so it's slightly different than our table, but it just means that there's a negative in front. Okay. So one important property about parabolas is their reflection property, and we use this quite a lot, especially in physics and engineering. So the first property is that if a light source is placed at the focus, here, this is the focus, the result is a focused beam of light emerging outward parallel to the axis of symmetry. So remember that the axis of symmetry for a parabola is the vertical line. Well, actually, it doesn't have to be vertical if your parabola turns sideways, but it's going to be the line that divides the parabola in half and passes through the focus and the vertex, right? Actually, that could be completely the way to describe the axis of symmetry is the line passing through the focus and the vertex, perpendicular to the directrix, right? So here, in this case, the axis of symmetry would be this line here, right? So if we had a light beam here, a light of some kind, and it emitted a beam of light and they hit into the parabola here, this is what's called a curved reflector or a parabolic reflector. And because of the symmetry and how the parabola is constructed with geometry, those beams are emitted and they will be parallel to the axis of symmetry. They're going to come straight out of that parabola. And an example of this in real life is our headlights. Almost all headlights are built in this way. The second property is going the reverse direction. So if parallel beams of light are coming in, if they're coming in parallel to the axis of symmetry here, they will hit the parabola and then they will reflect and converge and all meet at the focus here, right? So examples of this are telescopes and satellites, right? This is called a parabolic reflector. All rays entering are parallel to the axis and they reflect and meet at the focus, right? So that's how you take in data if it's coming into a satellite, for example. Okay, and here's a nice little picture from your textbook. So that's the intro to section 10.4. We're going to consider the other conic sections when we come back to class on Tuesday. We'll talk about ellipses and hyperbolas and then play around in polar.